translational degrees of freedom are 3. For non-linear molecules, rotational degrees of freedom are also 3. So the remaining degrees of freedom are the vibrational degrees of freedom. In case of water, the vibrational degrees of freedom, as it is non-linear molecule, are given by 3n minus 3 minus 3 or 3n minus 6 or 3 into 3 minus 6 is equal to 3. So in case of water, there are 3 modes of vibration. Now we show these modes and discuss their Raman and IR activity. The 3 modes of vibration for water are first mode is the symmetric stretching. Both the bonds expand or both the bonds compress. Let us suppose we have the polarizability ellipsoid is the minor axis, major axis. Now, as the bonds elongate or bonds expand, the polarizability increases. Therefore, the polarizability ellipsoid will become smaller in size, and as the bonds compress, the polarizability decreases and it will be represented by a larger polarizability ellipsoid. As the polarizability alpha changes during this vibration, hence this vibration will be Raman active. It will be Raman active. Now, as in this vibration, as the bond length increases, the dipole moment will increase in this direction, because the distance d between the two nuclei, two polar charged atoms, increases, and on this side the dipole moment will decrease. So there is a change in dipole moment. Dipole moment changes, hence this vibration will be IR active. This vibration will be Raman active because the polarizability is changing, and this vibration will be also IR active because the dipole moment changes. The second mode of vibration is called the asymmetric stretching. Asymmetric stretching, in which one bond expands and the other compresses. In this case, let us suppose it is the polarizability ellipsoid at the equilibrium position. Now, when the bond changes, when one bond expands, the direction of the polarizability ellipsoid changes. As the direction of polarizability ellipsoid changes during this vibration, therefore we say that polarizability changes and this vibration will be Raman active. However, if we consider the dipole moment, then the bond lengths are changing. Change in bond lengths will lead to change in dipole moment. In this case, the dipole moment also changes, hence it will be IR active. The second vibration is also Raman active and IR active. The third vibration is the bending vibration, in which the bond angle changes and bond length remains the same. Here we have water molecule. the atoms, hydrogen atoms are coming closer, the angle is decreasing, and in this case the hydrogen atoms are going away from each other. In this case, we have the polarizability ellipsoid for equilibrium position is shown as. Now, as the angle decreases, the polarizability also decreases, and we have a larger ellipsoid. On the other hand, as the angle increases, we have greater polarizability shown by a smaller polarizability ellipsoid. In this case, as the polarizability changes, alpha changes, hence this vibration will be Raman active. Raman active. Now, if we consider the dipole moment of the molecule, as the angle changes, the dipole moment will also change. Dipole moment changes, hence it will be IR active. So, all the vibrations in water molecule are both IR active and Raman active, and this observation shows, according to a rule of mutual exclusion, that water molecule has no center of symmetry, because it has the structure like this one. It would have a center of symmetry if this hydrogen was present in this direction, but it is not the case. As the hydrogens are present at an angle, therefore it has no center of symmetry. It cannot be divided into equal parts. Sometimes there may be molecules which may be both Raman inactive and infrared inactive. Likewise, we can not only find out whether a molecule is centrosymmetric or not centrosymmetric. By using this rule, we can also find out whether a given compound exists in cis configuration or trans configuration. That is, we can find out, we can solve questions, we can answer questions about the geometrical isomerism present in a compound. Let us consider the example of 1,2-dichloroethene. 1,2-dichloroethene has two isomers. The trans isomer and the cis isomer. If we consider the trans isomer, it has a center of symmetry. It is the center of symmetry. If we consider the cis isomer, then it has no center of symmetry, because it cannot be equally divided in two parts. This atom H and Cl are different, H and Cl are different, so it has no symmetrical arrangement about the carbon-carbon double bond. Now, as trans isomer is centrosymmetric and cis isomer is not centrosymmetric, for this compound, if we study the vibrations of molecules, then in case of trans isomer, if any vibration is Raman active, it will be IR inactive, and any vibration which is Raman inactive will be IR active, while in case of cis isomer, the vibrations will be either Raman active and IR active, or they may be Raman inactive and IR inactive. If this compound is following the rule of mutual exclusion, it will be trans, and if the compound is not following rule of exclusion, it will be cis. Allah Hafiz.